Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of hepatitis data. We have different patients and their symptoms, and at the end we have a column that tells us if the patient has hepatitis or not. Actually, if they lived or died. So we're really trying to predict if so they all have hepatitis. Sorry, and we're trying to predict whether they'll survive or not based on this class column here. So let's hop into the notebook. We're going to be, not logistic regression. We're going to be using a random forest classifier. And we'll be using NumPy and pandas for working with the data. For visualization, we're going to use this. I'm going to do some clustering today. So unsupervised learning, where we cluster the data using k-means. And then for that, we're going to need k-means and PCA so that we can visualize it. Then we will import models, train test split function and standard scalar from sklearn for pre-processing. Finally, we'll use the random forest classifier, which is an ensemble model from sklearn. Let's go ahead and import all of that and load in the data using pandas.readcsv. We can grab the file path up here. I'm just going to copy that in and take a look. Alright, so we have 20 columns, 155 rows, and we can see we have at least some missing values here. So we can check a little more with data.info, and you can see there's quite a few columns with missing values. Alright, so let's start pre-processing. I'm not going to do the full pre-processing here. What I want to do is just convert it to numeric form and clean up the missing values so that we can then cluster the data. So I'm not going to do any train test split or anything just yet. So let's create a function called preprocess inputs. This is going to take in a data frame, and right now all it will do is duplicate the data frame. So we'll make a copy and return that copy. So let's store the pre-processed version of data into x by passing data into our function, getting it back in x, and now this is the copy of the data frame we will perform the pre-processing on. So we can get x.isNA .sum. And you can see we have the number of missing values in each column with this. The reason the sum works is by the isNA matrix gives us a true wherever there's a missing value. They'll match up like that. And then by summing over the rows, by default this is axis is 0, which is the rows, it will count up all the trues in each column. And what's more informative than getting just the counts is getting the percentage of missing values. We can do that by taking the mean over each row. Because that will add up all the trues, then divide by the total number of rows, and we'll get the percentage of missing values in each column. So they all look reasonable. This is 0.6%, 6%, 7%, 3%, all through here. And then we have 18%. And generally, if you have a column over like 25% or so, it's usually a good idea to drop the column. You only have one example of that, which is the ProTime column, which is 43% missing. So we can consider dropping ProTime. We could also, because we have such a small amount of data here, it might actually be beneficial to hold this on. We should probably check this when we train the model. So let's include that into here. I'll just make a sort of temporary flag called drop ProTime. And by default, this will be true. Actually, it'll be false. Alright, and then first thing I'd like to do, because we have missing values in a whole different number of columns. Some of the missing values are in numeric columns, and the others are in, let's look at the sum again. Some of the others are in these Boolean columns. So how we want to fill the missing values, standard method is to fill with the mean of the column if it's numeric, and you can use the mode of the column if it's, or the median if you like, if it's categorical or Boolean in this case. Now, I'm going to do that. First, I'm going to fill the continuous features, the numeric features. So let's identify the continuous numeric features. So I'll just manually write this because there's not too many of them. Continuous features will be, I believe it's just these. Well, age is one. Right, we have age. then all of these are categorical. You can consider Boolean columns as categorical, even though we're just going to convert them into integer columns. But we don't want to fill with the mean here because they're not. The columns aren't supposed to take like 0.5. Like if we took the mean, we'd be dividing by we get some number between 0 and 1. So it's better to use the mode. And then all of these after this seem to be our continuous columns. The last two are again categorical, and then the class isn't actually a feature. That's what we're trying to predict. So let's grab these column names and put them in along with age. So I'll just go through and separate them like this. Whoops. Okay, like that. Alright, that's it. So we have our continuous features. Now we will fill the missing values. So we can take, first we'll fill the continuous feature missing values. So for column in continuous features. So for each of these, we'll take the column and call .fillNA, which will fill the missing values with whatever we pass in. Here we're going to pass in the mean of the column. So df subcolumn dot mean. And since these are all numeric, we confirmed there won't be a problem when we call .mean. By default, the mean function from pandas will automatically ignore missing values when calculating the mean, so we don't have to worry about that. And we'll store the result back into the original column. Then for the categoricals, for every column, this time not in continuous features, we want all the other columns that aren't continuous. So that would be df.columns.drop continuous features. So everything except continuous features. Then we take the column and call .fillNA. This time we pass in df subcolumn.mode. Now I would like to point out, if we take, let's use x, if we take the mode of a column, well, let's actually take the mean, let's use age. If we take the mean of age, it returns us an actual float, right? If we look at the type of this, we have a float. If we return the mode, I'm not sure why this is. Oh, interesting. It's actually returning 3 modes. Oh, right, because they're tied. Okay, now I understand. Right, because you can have more than one mode if they're tied. So it doesn't really matter. Maybe if we want to fill it more accurately, we could do a random draw. I guess we could. .sample1. We grab 1 each time. But the reason I'm saying to do this is because we have to use subscript of 0 to get that actual. Hold on. If we do it this way, that will actually return the integer. Now let's see, why is that not working if we do sample. If we sample 1, oh, because there's no 0. Okay. Dot values sub 0. That will give it to us. Okay. So I'll use a random state. This way we always get the same one. And if we do it for... Actually, do we want a random state? I don't know. Maybe I won't sample it. I want to be able to reproduce the results. So I'll just take the first mode that comes up. Shouldn't really be a problem. That way we can just do this. That will give us the integer. If we don't subscript, it gives us a series. Alright, so let's subscript here. Just take the first mode. If we don't care about reproducing the results, we could do a random... yeah, I guess we can do it. Okay, let's do it. Sample 1 with a random state so that we always get the same sample. And then call .values on that, and then take that value. That should do it. Alright, so we run this, and we look at x. Oh, sorry, I didn't actually set this equal to the column. Alright. Now let's look at how many missing values we have. They're all gone. We have completely dealt with missing values by filling the continuous columns with the mean and the categorical columns with the modes. So now I guess let's convert the Boolean columns into integer columns. This is very simple. We can just take, we say for each column in df.select dtypes. This allows you to take a slice of a data frame where the columns, selecting only the columns of a certain data type, in this case bool for boolean. And for each of those boolean columns, we're going to set the column equal to itself, but cast with .as type as a numpy.integer column. Now you'll see we have all zeros and ones where we used to have trues and falses. Alright, the last thing to do here is to encode this. The sex column has text in it, so let's turn it into a binary feature with integers. So encode the sex column as a binary feature. So let's take the sex column and call .replace on it, and we can pass in a dictionary to the replace function that has the mapping we'd like. So let's map female to 0 and male to 1. This mapping doesn't matter though, as when you're dealing with a binary column, female could be 1, male could be 0. This is the typical convention, so I'm sticking with it. Alright, so let's set that equal to the column and then see what we get. Alright, and now we have zeros and ones in there. So the label, if you're using sklearn, you can leave the label as text, and it actually makes it nicer when you're analyzing the results because you can see the actual label and it makes sense. If you're using a library like TensorFlow, you'll have to encode it as zeros and ones. And all the categories actually have to be equally spaced integers starting from 0, consecutive integers. But we're not using TensorFlow today. We're going to use sklearn, so I'll leave that the way it is. So last thing, let's shuffle the data because I'm not doing the train test split function. I figure we might as well shuffle since we will be using the train test split later, but I want to cluster the data, so I just want to shuffle it. Not like it really matters, but we can do this with df.sample fraction equals 1.0. So we're sampling 100% of the data without replacement. So we'll just do a shuffle that way and include a random state as well so that we can reproduce the results. And since we're shuffling rows, let's reset the index after and include drop equals true so that the old indices don't become a new column. Alright, and one more thing I want to do is to actually change the label name, the name of the column. Class is a reserved keyword in Python, and this can throw some errors if you have a column called class. When I was doing the, if you use query, if you try to query the data frame using this column name, it'll give you an error. So let's change the label name. Change label name. So df equals df.rename. We'll specify the columns argument with the dictionary to perform the mapping. We'll map class to label. So label is not a reserved keyword, so let's go with that. Alright, and then let's return x and y separately. So we'll split df into x and y. Y is what we're trying to predict, so that would just be label. And x is all the rest of the data. So let's drop label from axis 1, which is the column axis. And now we'll return x and y. We'll get them back over here, and we can now take a look at x. No longer the class is no longer here. The class is now in y. Oh, and I should say we are doing drop pro time, this thing. So let's code that in. Before we split, we'll include this thing. Drop pro time. So if drop pro time, that's the flag we have at the top, equals true, then df equals df.drop pro time. Axis 1. Okay, so right now it's on false. So we'll see how this affects the performance later. Okay. Alright, so we're ready. Let's do clustering. So we're using k-means, which is an unsupervised learning algorithm that will just, basically the way it works, it initializes cluster centers for however many clusters we like. That would be the k. In this case, let's make our k-means object with n clusters equal to 2. So we'll cluster the data into 2 clusters. We don't have many examples, so using too many clusters sort of weird. And then we'll fit this k-means object to x. So the way k-means works is it initializes centers of the clusters. It then calculates, it finds the nearest neighbors to the clusters. Let me pull it up actually, so we can check this sklearn. Okay, so here. Right, so basically the way it works, you specify the number of clusters, and it computes the distances between all the training examples and the cluster centers. And basically for each training example, whichever cluster center it's closest to will be classified as part of belonging to that cluster. After the end of the round, once all the training examples have been assigned to their clusters, the centers of the clusters are recalculated as the mean distance, or the new centers of the clusters that came about through the distance computation. So you're constantly updating the centers of the clusters until you converge into a nice clustering. So let's see. Once we fit this, we will have cluster centers, which is the actual coordinates of the cluster centers, and then labels, which are the classifications, the cluster classifications for each training example. So right here, we fit the data, we fit the k-means object to the data, and let's get back, we'll call it clusters. This will be the labels. I guess we can call it cluster labels. That comes from k-means.labels. We can take a look at that. You can see that each training example, each one of our training examples, has a cluster assigned to it now. And I'd like to visualize this. I'd like to see the clustering in some way. So for that, we're going to use principal component analysis for dimensionality reduction, because we can't plot a 19-dimensional graph. It just won't work. So let's compress it down to 2 dimensions using PCA. So for this, we'll make a PCA object with a number of components being 2. And we will take PCA and call fit transform on it to fit the object to x and then transform x. And that will reduce x down into 2 dimensions. So let's store the result in x reduced. And if we take a look at x reduced now, you'll see it's a NumPy array. So we have now 2-dimensional data. However, we want to turn it back into a data frame so it's nicer to look at. So let's wrap it with pandas.dataframe and pass in the index. I'm pretty sure we don't need this, but I'll just do it anyway. Index is x.index. It was already ordered from 0 until 155, or 154, so we don't have to worry. But I'll leave it anyway. And the column names here are going to be PC1 for the first principal component, and PC2 for the second principal component. And here we go. So now our 19-dimensional data has become 2-dimensional data, and each training example has 2 coordinates. So we can see this graphed on a 2-dimensional plot. Now, I also want to include more columns here. I want to label these with their classes, and actually also the clusters. So what I'll do is call pandas.concat to concatenate together x reduced, which is this data frame here, then y, which is the class labels, and then our cluster labels. This is actually still a NumPy array, so let's turn it into a series with pandas.series, and then give it a name, which will be cluster. Alright, and we're concatenating along axis 1, which is column axis. That means put them together side by side. Alright, and if we run this now, whoops. So here is, oh yeah, so this is our new x reduced. Let's save that in x reduced. And you can see XReduced now has the coordinates, the label associated with that example, and the cluster associated with that example. Now there's one more thing I want to do. Our k-means cluster centers, we can get that with cluster centers like this, is still 19-dimensional. Each center, there's only 2 of them because we specified two clusters, but each one has 19 numbers to represent it. So we're going to use PCA, the same PCA that we fit, to transform these cluster centers into 2-dimensional cluster centers. So we'll call those centroids. We'll use PCA.transform, so not fitting this time, just transforming, because we already fit it. Transforming, and we're going to transform k-means.cluster centers. And now, if we look at centroids, it's these guys, but now fit down into 2 dimensions. So we have the first center and the second center. Yeah, I think that's correct. Yeah, okay. So now we can plot it. Let's plot. So what I'm going to do, first we can just set up a new pyplot figure with plt.figure. Let's display it with a figure size of 16 by 10. And we'll use a scatterplot, so plt.scatter. We can start by just displaying the principal components, so the whole x, x-reduced, right? So we're displaying x-reduced sub 0. No, sorry, sub PC1. So PC1 will display on the x-axis, and x-reduced sub PC2 on the y-axis. So these are all of our training points. There's only 155 of them, but plot in 2 dimensions. So we've reduced the dimensionality down to 2 dimensions. Let's include some axis labels. So x label will be PC1. Y label will be PC2. And then we'll give it a title as well, which will be k-means clustering. So currently we're just looking at all of the examples as they are. Let's actually color code them by their cluster. So what we can do at the top here, we can separate the data into 2 sets. We can have the cluster 0 examples, and we can get this with xreduced.query. So let's see. xreduced.query allows us to basically ask a question about a column. We can try to find all examples where cluster equals 0. And that will give us such examples where cluster is 0. And you can see that's the actual data frame with the cluster 1s dropped from it. So let's use this down here. We'll save those examples here. And then we'll do cluster 1 examples. Just change these to 1, like that. What? Oh, okay. Right, so now we have these 2 sets of the data. So let's plot them separately with different colors. So instead of xreduced sub PC1, we're doing cluster 0 examples sub PC1 and PC2. And then for the second one, we're doing cluster 1 examples, like this. By default, the colors are blue and orange. I think that's fine. Let's give them labels, though. We'll call the first one cluster A, a second one cluster B. Like that. And since we have the labels, let's show the legend. And here it is. So we can see cluster A, cluster B. You can see where the k-means sort of came into effect. It found cluster center here and a cluster center here. We can actually plot those cluster centers since we did transform them with the PCA object. So for this one, we'll do plot.scatter again, but we're going to use centroids, which is our transformed version of the cluster centers. And centroids, we want to, on the x-axis, we're going to plot the first column of centroids. So all rows, first column. And on the y-axis, we'll take all rows, second column. We'll give this a color of light green. and size of 200, and give it a label as well, which will be cluster centers. Alright, and here you can see the cluster centers that were found via k-means. And it makes sense as well. Okay, so one more thing before we do the training. We can also plot the class distribution in 2 dimensions. So not essential, it doesn't really have much to do with the clustering, but it's still a cool thing to visualize. So let's take this whole block of code, paste it down here, except instead of plotting clusters now, I'm going to plot the classes. So we're going to query in the same way, but instead we're going to ask, is label equal to live and live and die, which are the 2 classes. So we'll call these live examples, and over here we'll call these die examples. And then we'll just replace these with live examples, replace these with die examples, and change the labels to live and die. And we don't need to plot cluster centers anymore. The title can now be class visualization, and we'll give these different colors. I'll make this one pink and this one purple. And now we can see the classes. So there's not really linear separability in 2 dimensions here. You can see if we were to do a linear separation, we would need higher dimensions to pull the data apart so we can cut it with a line or a hyperplane. But yeah, so you can see, I mean, they really have nothing to do with each other. It's just cool to see. Okay, so now let's do the training. So we're going to do random forest classifier, which is a ensemble method that creates a lot of decision trees in parallel and then uses a majority vote at the end to make the classification from all the trees. So let's do a train test split to start. Xtrain, xtest, ytrain, and ytest. We'll use the train test split function that we imported from sklearn. And now we want to split x and y, not x reduced. We're doing the original data that looks like this, right? Now we're going to split this and then scale it with a standard scaler to give each column the same range of values. So we're splitting with a train size of 70%, so 70% of the data is going to the train set. Then we'll shuffle the data again for good measure and include a random state of 1 so that the shuffle is always done in the same way. Then we'll scale x. So we're going to create a standard scaler, and the standard scaler will shift and scale the data so that each column has a mean of 0 and a variance of 1. Now we're going to fit the scaler to the train set only, and then transform both train and test set using scalar.transform. And we only fit to the train set because we want to pretend we don't have access to the test set at the time that we're doing the scaling and pre-processing, because that's the most realistic approach. So let's transform xtrain, and this returns a NumPy array, so let's turn it back into a data frame with the index equal to xtrain.index and the columns equal to xtrain.columns. We'll do the same thing for xtest, just replace all these with xtest. Alright, now we can do the training. So we'll create our model, which is a random forest classifier from sklearn. We'll fit the model to xtrain and ytrain, and we'll print out the test accuracy. We'll display the accuracy to 2 decimal places as a percentage and format that with model.score on the test set, xtest, ytest, and since it's a percent, let's multiply by 100. Alright, and we got a pretty good accuracy with 85%. So let's see now, okay, there is randomness here, because it is random forest. But let's see if this, on average it looks about 85%. We got 87, we got 82, but it's about 85. So let's see if dropping that original column has any effect. So we made this drop pro time equals false. Let's go in here and say drop pro time equals true. So now the pro time column is gone. And if we go back here, do the split and test, oh, it looks like our accuracy went up. So remember, we dropped it because we had too many missing values in that column. So if we fill the missing values with the mean, and there's a lot of missing values, then we're training on fabricated data, and it's not such a good thing to do. Alright, well that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.